So you're right, though. This is our last chapter. So sad.
I'm pumped. Get it over with.
Okay. So I think everyone agrees this is a vibration, right? And then I can jump up the vibrational energy ladder just by pulling it down even further, right? And the amplitude increases. So I think we're all on the same page. Now so it's kind of like a vibrational energy ladder, right? The more and more energy that I can give it. They can also call it a progression, right? Maybe this is the first vibrational energy level, right? Because this one doesn't exist. There's always some 0 point energy. Stop. There's always some 0 point energy, right? So this might be your 0 point energy. And then the next vibrational ladder might be this one, right? And this slowly goes up, and it's increments. So in this vibration, where's the turning point? What would you call the turning point of this vibration? Well, equilibrium, remember, is that position right there, right?
Would it be like there? There?
Yes,
There?
that's what I think. Because it's turning, it's actually physically stopping and going to the next. So there's two turning points, right? So even if it's a molecule sitting there, it's microscopic size in its quantum microscopic world, it has to have a turning point. Because if it's vibrating, it has to, right? It has to stop and go back. So that's kind of an important idea, because what we're going to be talking about are electronic transitions. And one of the things, well, let's start out with, if we're talking about electronic transitions, molecules are going from ground states to excited states. And what region of the electromagnetic spectrum are they absorbing to do this electronic transition? UV, ultraviolet, or visible, right? And so that's important. Another thing that I think is important for you to conceptually think about is vibrational transition. I just showed you, right? Okay, there's one. It started out at such an amplitude, now it's a bigger amplitude, but the frequency stayed the same. So that's a fantastic example of a vibrational transition. That's not electronic transition. Electronic transition is much more energetic or much less energetic? Much more energetic. Because what region of electromagnetic spectrum are we talking about here for vibrations? Infrared. We're talking about almost 1,000 times more energetic for electronic. Well, you got this molecule vibrating. That's a vibrational transition. What's an electronic transition then? It's not vibrational motion. It can involve colors, yeah. Well, your shirt's purple because of these electronic transitions. What's going on to absorb? Well, it's not absorbing purple. It's absorbing the complementary color, everything but purple. But what's going on in those little molecules to be absorbing these colors? What's an electronic transition? What is changing?
The electrons are being excited and whatnot.
Yeah, electronic has something to do with electrons. What's the, I think it's a tough one because it's an abstract idea in the first place. It's the idea of an orbital. What the heck is an orbital? We don't even know if they exist. It's just a model, right? We have these nice little models in the shelves over there. Ooh, this is what ethanol looks like. It's a model. We don't know, right? But it works. It works for organic, right? We can use it. So this electronic distribution, we like to think of electron density, right? There's some regions of the molecule where there's a lot of electrons, and there's other regions of the molecule where the electron isn't so often. Electron distribution. If you want to talk about orbitals, fine. You want to talk about molecular orbitals, fine. Bonding orbitals, molecular orbitals. It's electron distribution. That's what you're changing. Are the nuclei moving? No, they are bloody fixed. This is a very fast process and very energetic. Those nuclei didn't budge. They don't have time to budge. This electronic transition, boom, electronic distribution changes. That is what the Frank-Condon principle is all about. The nuclei don't have time to change. It's just this electron cloud, whatever word you want to put in there. Pi bonding orbital, anti-bonding orbitals, pi to pi star, whatever, right? The electron distribution is changing. Nuclei don't have time. So how do they explain that kind of thing? I like these plots because there's in a plot, just like a picture, you know, they say pictures are worth 1,000 words, but you almost got to have some words in there for this stuff to make sense. We've seen these kind of anharmonic curves before, right? What is the y-axis? Potential energy, exactly. The y-axis is potential energy. What's so potential about it? Potential energy. Of what? The answer is the x-axis. Yeah, kind of like this, kind of like displacement, right? I guess the best words would be displacement makes sense if it's a diatomic molecule, right? Because it's really just a separation between the two. But it's really molecular geometry. Where is all this? Where are all the nuclei? But I think displacement is probably what the book is going to be using, because all we're talking about all the time are these diatomic molecules. But essentially, it's just molecular geometry. Where are all the nuclei at? Okay. Like I said, we've seen these plots before. And you're supposed to have these vibrational energy ladders in there, right? And they got closer together as they go up. I mean, the book drew it better, right? But those are the vibrational energy levels. So you can put them in here too if you want. Now, if these are vibrational energy levels, what's this whole thing called? You can point at this line and say, oh, that's a vibrational state, all the same frequency. But this whole thing is a electronic state. The whole thing is an electronic state. So you can go from one electronic state to another electronic state. And again, what's an electronic state? Go back to those ideas of whatever words you want to put in there. Different electron distributions, right? Pi bonding orbitals, pi star, you know, whatever you want to talk about. Singlet states, triplet states. We've heard of these things before. So each electronic state has its own vibrational energy ladder. Now remember, I said that if you want when an electronic transition occurs so fast, nuclei can't move. They can't budge. So how do these things happen? Well, if you're going to be in the ground electronic state. Everything wants to be in the lowest energy level. So let's just start there. You're at the ground electronic state. Which vibrational level would you be in if you're in the ground state? Up here? Where's the ground state? Yeah, the very bottom one. Right, the very bottom one. Now, I'm putting my finger right here. And the reason why I'm putting it right in the center is it's a quantum mechanical phenomenon, I know. If I say Gloriana is a superposition, that means Gloriana's here. There's a 0.00, I don't know, probably a 0.500,000 zeros and a 1% chance she's also in Houston. And that number is going to get smaller. You know, the probability gets bigger and bigger and bigger the closer she is, because she's in her ground state. If you draw her wave functions, this great big hump right where she's at, right? And the tail's just kind of tailing off. And there's a little bit of area out there by Houston, but not very much. Which that's what a superposition is. So same thing's going on here. I picked the very center because I remember my ground state. I remember my wave functions. Remember, it looks like this with a very low particle in a box. Remember that talk? So you square it, and you get the probability of where it's going to be at. So most likely it's in the center. But it's a superposition of states. It could be really anywhere in there, but odds are it's right in the center. Okay, so we draw a line from here. This is where you're at. This is your ground state. And why? Just because everything we talked about, it's the lowest energy. You go straight up. Why do you go straight if you're going to do a transition? Because what can't change if you're talking about electronic transition? The nuclei can't change. So if you don't want the nuclei to change, you have to go straight up. There's our first word, vertical transition. Okay, so if we're going to do a vertical transition, we go up, straight up, until we hit a turning point. Now there's a lot of different words you can put in here. You can put in the word turning point, right? Because remember, what are these? This is a what state up here? Excited state. Is it an electronic state? How do you describe this? How many electronic states are drawn in that diagram? This is an electronic state, and that's an electronic state. Which one's the excited electronic state? That one. Excited electronic state, ground electronic state. There's two electronic states shown here. So we're going to start at our lowest of the low, ground state, and we want to describe an electronic transition, so we have to go from one electronic state to another one. That's why there's two drawn there. And vertical transition until, okay, now like I said, you can explain this several different ways. You reach a turning point of a vibration, right? Or you can think of it as the transition goes to a wave function that most similarly, is that a word? Similarly matches the vibrational wave function what's down here. But the same is really a turning point. Because if you're at, well, you see how it's right here? There's a lot of amplitude there. So this really is similar to that. They match. Constructive interference, kind of, because remember you got this wave property. But the point is they really match well. Or you can think of it as a turning point, right? So in this electronic transition, it goes up to here. Now it's up to at a turning point of that vibration. So now it's at a state where it wants this to happen. The potential energy wants this to happen. It's not happening, right? Because it's at, see what I'm saying? The molecular geometry didn't change. But once you undergo an electronic transition, damn, you better start vibrating because you're at the turning point of the vibration. Do you see that? So they don't call these really just electronic transitions. They call them, I don't see the word, vibronic transitions. Because that's really what they are. Because with this Frank-Condon principle, right, nuclei are fixed, electron distribution changes, but it changes, again, a couple ways. Either you can call it the turning point of the vibration in the excited state, or you can say, oh, there's a transition from the ground state to an excited vibrational state in that upper electronic state that most closely matches the ground state vibrational wave function. Okay? And notice how there's a bunch of them that are close. As you draw these lines, we could draw a lot more in here. It's much better illustrated here. Because it wouldn't have to go to just the ones really close to those vibrational energy levels above and below it that are really close. They really match pretty close too. So we can go there too, why not? Let's make the transition to go to those that are really close. And they call those vibrational progressions. That you don't have to go to just that one vibrational energy level. You can go to the one above it or below it. Because with this anharmonicity, man, they're not equally spaced between these vibrational energy levels. As you get higher up, they get even closer and closer. There's going to be a lot of wave functions that will closely match the ground state vibrational wave function. But in each case, it's a turning point of that vibration. So even though you're in a whole new electronic state, all the electronic distribution, the electron density is completely changed everywhere in that molecule. Instantly, without the nuclei even changing. That's why it's at a turning point. So it all of a sudden has to start vibrating with that new electron distribution. Okay? So we covered most of those words. Let's see if I skipped anything here. We could, I have absorbance, if you get an absorbance spectrum, what's the x-axis? Wavelength. What's the symbol for wavelength? That little lambda, right? A lot of times you use what units? Nanometers, right? Again, why? It's the most convenient unit because it's in the visible UV and ultraviolet. But anyway, if you had an absorbance spectrum that looked like this, then what that would look like, so again, that's what absorbance is. You have to start out at your ground state, right? And the ground vibrational state too. Vertical transition to the excited state, excited electronic state. But if there's no vibrational energy levels around it, you can't get a vibrational progression. That's what your absorbance spectrum would look like. A little blob, right? But when you get an absorbance spectrum,
you say that you don't get no vibration.
if you go right to here, that means there's no vibrational progression. If there's no vibrational energy levels that closely match this guy's wave function, or think of it this way, there's no vibrational energy levels that are close to this guy, that close to that turning point, your absorbance spectrum is going to look like that. No vibrational progression. But let's say there's a bunch that are really close, above and below. So it could also have a transition to those that are close. Well, then your absorbance spectrum might look more like, okay, where's the center? Here's the center. So that should still be your peak. But you're going to have some bumps on there. All right, you know how, remember seeing kind of like little ribs on your absorbance spectrum? Sometimes you might see like a shoulder or something, right? So we actually see vibrational progressions all the time. We just never really realized it. And remember, if you flip this guy on its side, take this whole thing. I don't think can I do that? Let's see if I can. Oh, I can't rotate, I don't think. Can I? Group. No. You know what I mean? I want to rotate the whole thing on its side. So then those are really then you'd see the energy levels. Okay. So let's see if you're following along here. In an electronic transition, the nuclear framework, using terminology that the book is using, the nuclear framework of the ground state, ground electronic state, is the same or different than the nuclear framework that's found in the excited state?
Different.
Same, because that's that Frank-Condon factor, right? It can't change. The nuclear framework, the nuclear geometry, the bond lengths, all these angles, all this geometry, all the bond angles, all the orientation, none of that can change.
So the nuclear framework is the same as what?
In the ground electronic state as it is in the excited electronic state during that transition. Now, that's not going to be like that for long, right? This is a static picture. Because we're at the turning point of a vibration. It's going to change immediately, right? It's going to start vibrating. You have a vibronic transition. Our Frank-Condon factor, there's a symbol for that. I think the book uses SV V prime, something like that. Maybe there's a comma there. But here's your vibrational quantum numbers. Let's clean this up. And if you want to describe or draw or give the mathematical equation for a vibrational energy level, you have to give the quantum number V. Well, in the ground state, it's V. In the excited state, V prime. So this overlap integral is, so that's what the Frank-Condon factor is. It's an overlap integral of just how well do these two wave functions overlap. And so your Frank-Condon factor is just that. I mean, if they are really, really similar, they have a lot of amplitude at the turning point, just like this is trying to show, a lot of amplitude at the turning point. You have a pretty big Frank-Condon factor. And the Frank-Condon factor will get smaller and smaller and smaller as the overlap, because there's less and less overlap, there's less and less the same. Okay, so here's a plot of these Frank-Condon factors, S, and they're just trying to say that, man, it maxes out where this x-axis is 0. Well, this x-axis is 0 where? If you can identify what these numbers are. I'm looking really at this, R minus RE. What are they talking about? The bond length. So RE is probably the equilibrium. Here's that equilibrium bond length, right? And so when R is equal to RE, then you get the maximum Frank-Condon factor. You get the maximum overlap. And that's pretty much what we've been saying. We're just saying that you go from the lowest to the low, right? Wherever they match up the best. Specific types of transitions. You've heard of the word chromophore. What's that mean? This is the carbon double bond in a molecule, is often called a chromophore, because it really likes to undergo this transition. Here's your pi orbitals, above and below the two nuclei. Right? There's a carbon, there's a carbon. So it goes from a bonding to an anti-bonding type molecular orbital. So, and this is just talking about the carbon double bond, but this is what's doing the interaction. This is what's absorbing the light. This is the chromophore. The chromophore is the portion or the part of the molecule that's absorbing the light, right, for this electronic transition. So that's really different than, I think, that's really different than when you think about infrared spectroscopy, right? If you have a vibration, pretty much that whole molecule is right doing something. So chromophore really is a word that's, I think, is most used on this electronic transition kind of talk. Here's another chromophore, carbonyl, right? I guess you have, so I don't think we need to talk about that anymore. The ligand field parameter, I think this is, I didn't bring those in. I was in a meeting, I didn't have time. That's a nice plot. Well, maybe you guys can tell me, or you can tell everybody else. Where have you heard the word ligand? Inorganic chemistry, okay. And what type of compounds? Metallic. So you got a metal and you got all ammonia around there or something, right? You have a whole bunch of ligands, right, with a metal in the center. So this ligand field splitting parameter, the book is, I think, just throwing a lot of terminology at us because they're not going to have us do all the math, which is fine, right? Let's just go through the terminology then. So what they're going to do is they're going to take the, is it the atomic orbitals? Right, you got your metal. I'm trying to remember this. You have a bunch of ligands around there. This is probably a little simplistic, but that's the idea, right? And this ligand field splitting parameter, we're talking about this too much. There, you get the atomic orbitals from the ligands, and then the d orbitals from the metal, and that's what they're using to describe what's going on with these types of compounds. Anyway, whatever. So the Laporte selection rule, I think, is kind of interesting, though. In a molecule with, let's see if I can avoid having to write this word. This symbol is for what type of symmetric operation? Little I. Center of inversion. Right. Here's a molecule that has a center of inversion. Right? You can reflect through it, and you get the same thing. Right? Nothing moves. So in molecules with a center of inversion, these types of transitions are not allowed. Now, what was this G and U stuff? Parities, Gerada and Ungerada, right? And if it had a center of inversion, all these molecular orbitals were supposed to have Geradas, G's, and U's on them. Okay, and so if the wave function sign didn't change, it was Gerada, kind of like the color. That's what the colors meant. Bright color was plus, dark color was minus. The wave functions. And anyway, these aren't allowed. However, with the Laporte selection rule, even this will happen if the vibration removes the center of inversion. And that's what they're trying to say, that in this vibration, right, this atom goes down. They all go down, right? This guy's going up. Or what's he doing? Just pull this guy down so that everything is pulled down. The center of inversion's lost, right? Because this is going to be down. These are going to be up. You try to reflect through the center. There's nothing there. So you lose the center of inversion with this vibration. And what the Laporte selection rule says is, hey, if you have a vibration that makes you lose the center of inversion, well then, forget this. These transitions will occur. In other words, these vibronic transitions will occur. Okay. So even with a molecule that has a center of inversion, and these transitions are not supposed to occur, well, remember these are vibronic transitions. So if that vibration loses the center of symmetry, it'll still occur. Oh, and they like these ligands so fine. The ligand to the central metal. I'm trying to transfer an electron there. Transfer an electron from the ligand to the central metal. Okay, and LMCT. This stuff is really detailed, and I don't know how much the homework is going to get into this, but yeah, there it is. Ligand to metal charge transfer transition. So, or you could have it the other way around, right? The metal can give its electron up to the ligand. So metal to ligand charge transfer. Okay, so anyway, I don't know why they got into that so much, but now we're getting back to, I think, things that are a little more general instead of just talking about ligands, metallic compounds. The fates of electronically excited states. So I guess there's two ways to get back to that ground state, radiative and non-radiative, right? So radiative means what? So if you want to return to the ground state, radiative. What does that mean? Or non-radiative. Decay makes sense, because the energy is going down. If it's a radiative process, it means that this excited molecule does what to get to the ground state? Emits light. Emits light. Non-radiative, well, it doesn't emit light, but somehow it's still at the ground state. It ended up there. So I guess getting to the ground state by emitting light kind of makes sense. Just shoots. We'll talk about it in more detail. But non-radiative, where does that energy go? So you're in the ground state, you're going to the excited state, it's at a turning point, you know, this thing's all vibrating. Where does this energy go? How does it go from this excited electronic state with even this higher vibrational energy level, right? It's not even at the ground vibrational level in the excited state. It's way up there somewhere. How does it end up way back down here without even emitting light? Give up heat. Now, what is heat?
Energy.
Yes. And this, now,
Chaotic.
yeah, keep the thought on this molecule.
Is it just transferred?
How? Yeah, what is it doing? What are these molecules doing?
Rotating, vibrating, oscillating.
All these things. They're flying through the air. They're rotating. They're vibrating. All these things, but have this energy disperse. And it's just going to jump down the energy ladder. It's going to go from one electronic state to the other one, all just by increasing this random chaotic thermal motion, which is what you just said. Rotation, vibration, right? Translational motion. Just disperse the energy chaotically. Very random motion. Okay. So fluorescence. Okay. So what I like what they're doing here is notice how they're being consistent. How their absorption line starts where? They do it in a very particular way. Because absorption is this one. Starts in the very middle of the bottom of the vibrational energy ladder of the ground state, ground electronic state, right? Perfect. They're being consistent. I love it. Then it's vertical. And again, why is it vertical, Jeffrey? Why is this a vertical line? They're talking about absorption.
Because it's a turning point straight up.
The nuclei, so the nuclei don't change, exactly. So it has to be vertical. This is a what type of transition? Yeah, vertical transition. It's a vibronic transition. It's an electronic transition. Both of those words work great. This is a vibronic or an electronic transition. Vibronic is a little more explanatory because not only is it electronic, it's also vibrational all at the same time. Okay, so we're trying to describe fluorescence. What are we trying to do? We're trying to describe fluorescence here, right? Yeah, we're trying to describe fluorescence. Okay, so for this transition to occur in the first place, from this state to this state, it's called absorption. Is that allowed or not allowed? What would it have to be? It would have to be allowed, otherwise absorption is not going to happen in the first place. So it has to be allowed. This has to be an allowed transition. So very often, it's just nature, man. This is what happens almost all the time. Singlet state to singlet state. You don't change, the spin doesn't change. Delta S equals 0. Remember that big, I don't know if you remember this kind of stuff, right? The total spin can't change. Okay, so like singlet state to singlet state is very most often the most common thing. Okay, now you're up here. And what are they showing here? What's all this stuff going down here? I can't even read that.
Radiated?
Oh, it's
Radiation?
radiationless decay, right? And what do we say that is? Yeah, through all the rotations, vibrations, translation, with all the surrounding molecules and this container, all that stuff. Energy is just slowly lost. Right? And it's, albeit it's packets of energy that are lost. It's not, it can't just dish out any energy at once. But the point is it ends up down here. Okay, now to go from here to here, right, it emits this photon. Right? Now, one thing that I think is kind of, okay, it emits a photon, and then notice how I could have emitted that. In fluorescence, is it always going to be right here that you're going to emit from? According to this picture, I mean, we don't know any different. We don't know any different. Yeah, it is, and it is. You're not going to be up at some higher vibrational energy level and then boop, pop down to the bottom electronic state. There has to be something that's going to stop you. There has to be something. There's no reason why you should emit up here. I mean, you just balls roll downhill. It's just the natural and the easiest thing to do. So this energy is just dissipated until it can't get dissipated anymore. I mean, it's at the lowest vibrational energy level. It's at the lowest vibrational amplitude it can have. It can't have any lower vibrational energy level. Before it was like this, but that's really easy to give up because you just ram into Gloriana and then you're out like this. You give up this energy really easily. It's very natural and very, very fast. You end up here. But now your electronic distribution is messed up. You can't get any lower energy. So what it wants to do is it wants a new electronic distribution. So it does it. But it only does that from the bottom vibrational energy level. Okay. So it emits that photon that's equal to that energy difference. Now notice what I think is kind of cool here is that it doesn't have to end up here. There's some vibrational energy levels that very close, the Frank-Condon factor. There's some Frank-Condon factors that are pretty appreciable for the vibrational levels that are close to this, right? The overlap, the wave function that's here is very similar to the ones that are close to this one. So it could go from to the ones that are closer. There could be a vibrational progression again. Now you shouldn't call it absorption. What do we call it? Absorption progression or something? Well, we call it vibrational progression. Hey, even better. So it goes either way then, right? Vibrational progression. So when you do absorption, this vibrational progression is of the ground state or the excited state in absorption.
The ground state.
I've always wanted to say ground because it makes sense, right? You're at the ground state and you're going to the excited state. It's absorption. This is where you're starting out. But what are you actually investigating when you're doing an absorbance spectrum? You have to start down here. And then where do you go? You go to all these different vibrational energy levels in the excited electronic state. So you might go here, you might go there, you might go there. So here, you might go here, you might go here, you might go. Now there is one that matches the best, that's for sure. But they're on both sides. So you are actually investigating what with absorbance spectra? Excited electronic states or ground electronic states? You're actually investigating excited electronic states. It is the opposite of what you would typically think or guess. And then with emission, look what happens with emission. You're not, it's the same idea. You're going to emit from that bottom vibrational energy level. Just like in absorbance. Absorbance is initiated from the bottom vibrational energy level. That's what nature is. Nature is always at the lowest energy. So if you're starting out here, so fluorescence is going to investigate the what state? You go here, you go there, go with this one. Fluorescence investigates the ground state. You see that? Because fluorescence, you have no choice. Fluorescence has to initiate right here. So it could the transition could go to any of these vibrational energy levels. There's your vibrational progression. But where's the vibrational progression you're investigating? The ground state. So fluorescence investigates the ground state. It's just the opposite of what you would think. And there's no reason, and they're not, I guess I like it, they're not mirror images of each other. I mean, they could be different vibrational progressions, so there should be different peaks. Just like they're illustrating there. What time did we start? I always lose track of this. I don't know why. 45 is such a hard time for me to remember. Okay. So we have 20 more minutes.
No.
Okay. Let's see. So now we talked about fluorescence. Okay. I have these two are DWAs. Should be DOAs, dead on arrival, right? But what's the overall time frame for this process to happen? How fast is this? Somebody know? It would seem like it, but it's really not. We have instrumentation that can analyze this, and you can do research with it. In fact, I think I told you all that. But the point is on the order of nanoseconds, a billionth of a second is about how fast this stuff happens. Is this the glow-in-the-dark toy stuff? No, that's phosphorescence. Something has to happen to really slow this down, really slow it down. Okay, we talked about absorbance. Is absorbance an allowed transition? Yes. Is fluorescence an allowed transition? Yeah, it has to be, because if absorbance is, fluorescence is, because they're the same electronic states, right? They go in from this electronic state and then back down. The same one. If it was allowed in the first place, it's allowed the second time. Okay, so to really slow it down, look at this picture. What changes? We need an electronic state that has a different spin than the ground state. You have to. And if you look at this picture up here, how the hell could that even happen? There's only two. So what has to happen is you need a third electronic state, but more so, you need, the fancy word is intersystem crossing, but you need a vibrational energy level. Now first identify those three electronic states. You've got your singlet ground state. You've got your singlet excited state. So there's where your spin won't change. You get absorbance going, just like we did before. And everything should be hunky-dory, except there's an electronic state whose vibrational energy level, one of them, somewhere in its vibrational ladder, man, it just perfectly matches that in the singlet state. Perfectly matches it. That wave function is, they're identical. So without even knowing it, this molecule thinks it's in nature, just going down the vibrational energy ladder, just dissipating all of its energy. All of a sudden, it's got an electronic distribution that's that of a triplet state. It's energetically impossible to transfer its energy to the singlet state. It can't happen. It's not allowed. Well, for something that can't happen and not allowed on the microscopic level is how long? If nanoseconds was allowed, what's not allowed? Yeah, I'd like to say centuries, but that ain't it. The instrumental people should remember. How long is the lifetime for phosphorescence? It's on the order of seconds, minutes, or milliseconds, but nothing faster than milliseconds, really. Otherwise, that glow-in-the-dark toy isn't really a glow-in-the-dark toy. It's gone before you can even shut the lights out, right? So phosphorescence is typically seconds and minutes for lifetimes. Well, milliseconds too, but okay. So this is where I had some nice pictures. So a lot of it that they understand with intersystem crossing is with heavy atoms, and spin-orbit coupling is the technical jargon. But spin-orbit coupling. Spin-orbit coupling. Do you remember, I should get my email. I've got 20 minutes, right?
Oh, we have like 2.
Oh, we've got so much time. I'll just have to show you next time my nice pretty pictures that I found. Okay. So we got quite a ways.